What I thought we would do today is to discuss the first assignment. Were all of you able to do all the problems? So what's the answer to the first one? So we had, basically this is sort of practice in network analysis, but it does have some point. This was the problem, right? Let me call it GM, GDS, CL, CC and maybe C1 or something. RS, okay. So, what is this? Does it have any relevance to any circuit you know? So, this actually is a MOS amplifier. And how do you go about solving it? Yeah. What did you get to be the answer? First of all, let's try to get as much information without doing the analysis. I said, I want you to evaluate V0 by Vs. What is the DC gain? Huh? Minus GM by GDS. Isn't it? Or it was called RL maybe. It's minus GM RL. Okay. So if you remove all the capacitors, Vs appears at this point and you simply get GM divided by the conductance, but the sense of the current is flowing upwards through the conductance, so it's minus. So whatever answer you get, you should get DC gain to be minus GM by GDS or GM by GL. Okay. Then what else? What else can you find out from this? What's the order of the transfer function? Why? Two state variables. I mean, how many capacitors are there? 3. So, does it have anything to do with the order? Okay. So, there are actually 2 independent state variables. So, the order is 2. But is that familiar to everyone, the concept of independent state variables? What is the order you can have with 3 capacitors? Maximum of 3. Okay. So, you can definitely say that it's not 4th order. But beyond that, you have to do a bit more analysis. Does the order have to be anything? Can you have 0th order with 3 capacitors? Or can it be 0th order, 1st order, 2nd order? Huh? Okay, let's say that we do not do something so nasty to the capacitor. It can be 1st order. All 3? Yeah. So first of all, there is this stupid thing that you can do, that you put all 3 in parallel and it becomes 1 capacitor, right? So can you have 3 capacitors which look distinct and still have 0th order? Or you can have 3 capacitors in parallel or series. I think that will also give you, even in series you can get 1st order or any order. So you can get 0th order by doing this, right? What's the transfer function? What is the transfer function of this? Huh? It is some ratio of capacitors. So you can get 0th order. The only thing you can say safely is that it's not more than 3rd order. But by looking at it a little bit, but perhaps you can say it's a 2nd order system, because you have one loop of capacitors, and if you know the value of voltages across these 2, you can find out this one. But whether this itself is independent from this, it needs a bit more analysis. But in this case, it is 2nd order. That's the answer. Okay. Is there some particular case for which you can write down the transfer function straight away without having to write all the node equations and so on? CC is 0. Okay. CC is 0. So if CC is 0, that means CC disappears. So why does it make it easy? So what is the transfer function in this case? So in this case it's very easy because the two poles are separated. You have the transfer function of the first part. What is this from Vs to this point? And what's the transfer function between this voltage and the output? So this is basically the current of Gm times this Vg or Vx will flow here, and that flows through the parallel combination. Okay, so this is Gm divided by GL. Let me just change the notation. GL plus SCL, which can alternatively be written as the product of two terms, okay, and the poles can be written by inspection. This is okay. So again, this is some limiting case that you can check. In fact, you don't even have to write this down. After some experience, you know that if CC is 0, you know that these are the poles. So whatever answer you get for the more complicated circuit, if you put CC equal to 0, you should get this. So these are all things that you need to do, first of all, for sanity checking your answers, as well as to develop some intuition about the circuit. Okay. So we know what the DC gain is. We know that it has two poles. Okay. And we know where the poles must be in absence of CC. Do you have zeros? Yes. I mean, I think you already calculated the answer and you do know that. But why do you suspect that there should be a 0? So typically you end up getting a 0 when you have a transfer function like this. Let's say you have two paths that combine. Okay. You can expect something to happen to the numerator. Again, it doesn't not necessarily always give you a 0. Okay. But you can make it so that it doesn't give you a 0, but you can expect there to be some 0 when you have multiple paths combining to give you the output. Okay. So I think that is probably all that we can say, but without doing some serious analysis that we can do now. Does anyone remember the answer? We will do the analysis. That's okay. Did anyone have difficulty setting up the equations for this? So I set up the node equations. This is Vg and this is Vout. Okay. So what is the equation at this node? This one first. I like to use conductances because it comes out to be the sum of terms in nodal analysis. And what else do you get? Is it okay? This is okay? What about the second equation? The equation here. What's the coefficient of Vg in this case? So in each case, what I have drawn here on the left hand side are the currents flowing out of that node, and the right hand side is the current source that's injected into the node. Okay, effectively, that's what it is. So I can transform this into Vs times Gs and the conductance Gs in parallel. Okay. So the current source appears here, it's flowing into the node, and the total conductance is SC1, total admittance is SC1 plus SCC plus Gs. Okay. Is this part clear? Okay, what about the next equation? What's the coefficient of Vg? Huh? First of all, you get minus SEC because of this, and because of this control source, you get plus GM. Again, we are summing the currents flowing out of this output node. Okay? And the current out of V out, what do you get? This is CL, SCL plus SCC plus GL. And what's the right hand side? Huh? 0. There is no independent source connecting here. So I have to solve these two. Okay? What is the solution for V out? So maybe I will do it a little more systematically than this. Okay. So if you were to use Kramer's rule, you can set up this. So this is some admittance matrix times the voltages equals to some source vector. Okay. So in the solution, what I have to invert this, and in the solution to V out, I get the determinant of this matrix in the denominator, right? And what do I get in the numerator? I substitute this vector for the second column because I want V out is the second element of the vector. Okay. So anyway, you can solve it any which way you want, but it's always best to be systematic. Okay. So if I remember correctly, the terms were, the first one will be 0 and okay, and here we get what was the term here? SC1. Okay. Is this what we get? Huh? What cannot be minus SEC? Oh, okay. So what do we do about that? So you are complaining about this term. Numerator. Oh, actually, what is the... So VSDS, sorry. Yeah. So I didn't substitute it, evidently. Obviously, it's supposed to be dependent on Vs. In fact, this is not V out by Vs, it's the solution to V out. Okay. So here, if you compute it, we'll get okay, and the CC square term will get cancelled out. Okay. So V naught, V out by Vs will be minus so is the DC gain correct? So you do get, I mean, if you put S equal to 0, you get Gm by GL, right? So anyway, let's rewrite this as Gm by GL. It is Gm by GL, or is it not? It is, right? So you get Gm times GS divided by GS times GL. Okay. And something here. Okay, we'll look at it. Actually, there is no room here, but the last part is plus 1. Okay. It turns out to be this. Maybe. This is the transfer function. Okay. So, where are the poles and zeros? Where are the poles and zeros? The 0 is at minus Gm by Cc. It's in the right half plane. Okay. So we'll see the implications of this later. In fact, we'll use this analysis heavily when we come to common source amplifier as well as when we come to compensation of op amps. Okay. So in fact, this analysis will be the basis for finding some method of compensation. It can be thought of as a basis for that. So I urge you to pay attention to the results of this, not just calculating it, but also figure out what happens when you change different quantities. Okay. So it has a right half plane 0 at basically at Gm by Cc. Okay. And where are the poles? We can use the approximation, otherwise it gets too messy anyway. So, if you have a quadratic equation, I said one of the poles is at minus this coefficient divided by the fixed term. Basically, I am combining this, the last term with this one. Okay. So, does it make sense? What's the meaning of this term? Does it have any significance?
First term is the pole intrinsic, which is the C1 into capacitance and 1 plus GMR, gain times Cv.
So, actually, yeah, in particular, this term is Cc times 1 plus Gm by GL. What is that? Miller multiplication of Cc. Okay. But we have some extra term also. Why is it not exactly just this part? Why do we have the extra term? problem is the regular Miller effect calculation assumes an amplifier with zero output resistance. If you have CC, you will simply see CC times 1 plus the gain, 1 minus the gain. Okay. So if you have a negative gain amplifier, it looks like CC has become much larger, or the loading is larger than CC. Now in our case, we don't have zero output impedance, so you have some extra terms. But largely it is basically, if you look at this, this is the capacitance that you have connected here, plus the Miller multiplied capacitance, divided by the conductance, you see. Okay? Is this okay? So, across the conductance GS, you see C1 of course, because it is directly connected, and you see the effect of CC, which happens to be a Miller multiplied version. Okay. So that is largely what forms the first pole. I mean, if CC is significant. Otherwise, because we have an imperfect amplifier, we have this extra term also. Okay. So this is Miller multiplication of CC. The gain is minus GM by GL, so you get 1 plus GM by GL times CC. Okay? What about the second pole? So, did you guys recognize it as the Miller multiplied capacitance when you did the analysis? It is pretty clear, right? What's the second pole value? Again, using the same approximation. We have the coefficients here. This is what the second pole turns out to be. Is there some interpretation you can give to this? So let's take one particular case where, okay, and also CC happens to be, this is quite reasonable anyway, this is true in most cases, hopefully, and CC also happens to be much more than C1 and CL, okay. What is the value of the pole? Huh? GM divided by C1 plus C2. Where is C2? C1 plus CL. Okay. Does that make sense? So under this condition, it is so a pole is like ratio of some conductance to some capacitance. Okay, I mean the expression can come out in any which way, but you can expect some conductance to be across some capacitance. If you do have that, you have the pole of, if you have a conductance G across a capacitance C, you can sort of expect a pole of G by C. So, do you see this anywhere? So, in this case, this is the conductance, this is the capacitance. C1 is not the output capacitance. Where do you see this picture? Where you have a conductance of GM and C1 and CL across it? I mean, I have to first of all say that not always can you reduce things to this type of picture, but if you do, it will be better, right? In some circuits, it may not be possible. Maybe it's a result of interaction of a number of things. But in this case, the pole has come out to be some conductance divided by some capacitance. So, do you actually see that in the circuit? What's that? No, I know, but where do you see the conductance of GM? Why do you see it? That is there some physical interpretation you can give to this expression? That's the question. Okay.
Maybe the RL is very high, the current is flowing from GL into the AM.
No, RL is very high. That we have already assumed, right? In fact, this one is not dependent on RL.
CC was a short.
Yeah. Yeah. So, is that clear? His answer was that the CC is nearly a short. So, what happens to the transconductance? If you have a transconductance GM, okay, this is the controlling node, this is the output. You short the controlling node to the output. What does it look like? If you have V here, GM times V will flow. It looks like a conductance of GM. Okay? So in this case also, if I simply short this, I have a conductance of GM and I have neglected GL and GS across it, that's okay, and I have C1 and CL across it. Okay? So that's how you get GM by C1 plus CL. Okay? Is this clear? CC behaves like a short, which basically turns the transconductance into a conductance of GM. And across that you see C1 and CL. So if CC is very large, CC does not influence the pole. Okay? No, not necessarily. This is only in this approximation. Okay? In fact, first of all, even to solve for P1 and P2, we have assumed that the two poles are far from each other. That may not be true, but if that is true, these are the answers. Okay? And it turns out that later, when we look for more interesting cases, that is the more interesting case, when the two poles are relatively far away from each other.
The gap is short.
Huh?
The gap is short.
Yeah.
GM primary C1 and CC.
C1 and CL, not CC. CC is the one that is short.
And if there is one resistance, would that affect the...
Yeah, I mean, basically it could be, if you have extra resistance, it will be GS plus GL. But I have just neglected these terms in comparison to that. Okay. So if I short out GM, that's the picture I have. I have GM, a conductance of GM, a conductance of GS, and a conductance of GL in parallel with each other. And across the whole thing, you have C1 plus CL. Okay. So let's not do such a crude approximation. Let's do something a little better than that. I can also write P2 as okay. I divided the numerator by C1 plus CC and the denominator by the same thing. Okay. So in this case, beyond making the approximation to compute P2, I have not made any further approximation. This is the same expression as this one. Okay. What is this? Again, you can neglect GL and GS. I am not too worried about that. Okay. What is the rest of the stuff? As usual, it is some conductance divided by some capacitance. So the question is, do you see the conductance somewhere and do you see this capacitance somewhere? What is the denominator? Huh? So C1 and Cc are in series and the series combination is in parallel with Cl. Okay? Is that there in the circuit somewhere? That is how it is in the circuit, right? So in fact, if you look from the output side, I have Cl, I have Cc and C1. So if I look from this side, the capacitance I see in fact is Cl and Cc and C1 in this combination. Okay? What about the conductance? We will deal with all of these things in detail, but since we have the opportunity to discuss it, we can do it now. Okay. And that way, hopefully, the result will be in your mind for a longer time. Okay. If you give some meaning to it. Exactly. So if you take a conductance, this is the controlling node. Okay. Now you don't short this to this, but you have a capacitive divider. Okay. So if I apply a voltage V here, what is Vg that appears? So V times Cc by C1 plus Cc. Is this part okay by everyone? So what is the current flowing through this? The whole thing multiplied by Gm. So the conductive part of the current that is flowing here is this conductance, okay, times the voltage. So that's the conductance you see. Okay, you see this conductance plus you also have a conductance GL. So that gets added. Now you also have a conductance on this side, so that gets added in a slightly complicated way. Okay. But I mean, because of this conductance, you also get some conductive current. That is, what do I mean by conductive current? The current flowing there and the voltage are in phase. That is a conductive current. If they are 90 degrees from each other, it can be either capacitive or inductive. Okay. So the numerator that you see is Gm times some ratio, and that ratio comes because of capacitive division plus GL. The GL is across it anyway. Okay, and the denominator you see is the total capacitance you see from the output side. You also get this because you have connected another conductance to the input side. Okay. So, but this is the dominant term, right? The first one is the dominant one. Okay. Is this clear? So you have a conductance, a transconductance in feedback with some ratio. So you get a fraction of the transconductance as the conductance. That divided by the total capacitance you see is the whole. Okay. Okay. So if Cc increases, does P2 move to higher frequencies or lower frequencies? So again, you neglect all the insignificant terms. Okay. What do you think will happen? Lower frequencies. I mean, you should also give a reason. Anyway, here you are just looking at the expression and saying whether it increases or decreases with Cc. So if Cc increases, does it move to lower frequencies or higher frequencies? I mean, when I say lower frequencies, I don't mean becoming more negative. I mean the absolute value of P2, right? If the absolute value of P2 increases, it goes to a higher frequency. So you ignore this minus sign and then figure out. That is it. Huh? Lower frequencies. Why? Yeah. What? So, but how does it say that it is moving to lower frequencies? No, why? It can go and stop somewhere, right? Why does it have to go all the way to infinity? What is the pole value of CC 0? I mean, with this expression and neglecting everything that we find inconvenient, 0. And if CC is very large, so what happened? Is it moving to lower frequencies or higher frequencies? It's clearly moving to higher frequencies, right? And you can see from this term also, CC influences this ratio. If CC increases, this ratio moves closer to 1. Okay? So the numerator increases, the denominator increases also, but only one part of it. Okay? It's the same ratio in fact, it's CC by C1 plus CC. So this part increases, this part remains the same. So the denominator does not increase as much as the numerator. Okay? So as CC increases, the pole does tend to move to higher frequencies. Okay? Of course, when CC is 0, this expression is 0. At that point, the approximation to calculate P2 has broken down. So that's not a useful thing. But just by looking at how much this increases and how much the denominator increases, you can say as CC increases, the second pole increases. Okay? The only thing I can say is that so if CC is an open, okay, what is the pole on the output side? CL, 1 over CL times RL, right, or GL divided by CL. If CC is a complete short, it is the output conductance is increased, right, the conductance on this side. So it is GM plus GL divided by CL. So that's how it has moved to higher frequencies. Okay. Is that okay? The question was why does it make intuitive sense that the pole moves to higher frequencies with CC? If CC increases, the conductance on the output side increases because of feedback around this GM. So the capacitance is more or less the same, let's assume. So because of that, the pole does move to higher frequencies. Okay? Is that convincing? If you didn't have CC, the pole was GL divided by CL. Okay? As we see here. If you have CC, then it does change. I mean, it does increase, in fact. It is closer to CL divided by, GM divided by CL. So roughly speaking, it moves from GL by CL to GM by CL. Okay, so it moves to higher frequencies. What happens to P1 with CC? So we have the expression for P1 here. Does it increase? Does it move to higher frequencies or lower frequencies with increasing CC? Clearly to lower frequencies, right? Because the denominator goes on increasing. So very quickly, what were the poles without CC? You have some DC gain, the magnitude of the DC gain. So here I am plotting the Bode plot, okay? Magnitude of the gain. The DC gain is GM by GL. Where are the two poles without CC? So let's say this is GS by CS or C1, I think. And the second pole? It could be higher or lower. I am just drawing it this way, okay? GL by CL, okay? And it does this. So as CC increases, this moves outward, this moves inward. Okay. So the response looks more and more like something like this. It looks more and more like a first order system. Is that okay? So what use is this? This is what is used for compensation. Anyway, we'll see the details later. But this was just to give you a feel for why the results come out the way it is, and also why the CC in particular is a useful term. So by making CC larger, you can make it look like having one low frequency pole and a high frequency pole like very high. Okay. Any questions on this? So again, as far as this assignment was concerned, it was more or less a practice for circuit analysis, but please do keep the result in mind because we will be using it repeatedly afterwards. Okay, and this phenomenon of one of the poles moving higher and the other one moving lower is known as pole splitting. Okay. So this is the basis for Miller compensation of op amps. Shall we move on to the next one? Yeah, 0 was there, that's correct. So the 0 will move to lower frequencies if CC increases. Right? See, 0 is a result of if you have some voltage at this point, there is some current in phase with the voltage through the GM, and there is some current 90 degrees from the voltage through CC. Okay. So because of this, you get a 0. You get to out of phase addition. So if you have increasing CC, the part of the current through the capacitor increases. So the frequency at which it becomes significant moves lower. Okay. Anything else? So we'll discuss this in detail when we come to common source amplifiers. Okay. So that's the equivalent circuit of a common source amplifier, and that's what that's the result of the analysis. The second problem was there's no transistor there. Okay, so what is this? This GM can be thought of as a transistor. So this will be the drain, gate and source, in which case this will be, let's say I call this Vx, that's really the VGS of the transistor, and this is GM times Vx. The question was what's the input impedance of a device like this, a circuit like this? What is it? What is special about it? You get a negative resistance. Why does that happen? Yeah, it's because of the current source, and one way to see it, it's sort of contrived, but if you force a current I, okay, it produces a voltage V that is 90 degrees lagging from the current I. Okay. So, and this voltage produces a current. So, if this I is at 0 degrees, this voltage will be at what angle? Minus 90 degrees. And that current will flow through this capacitor. Okay. So, what's the voltage, angle of the voltage here? The part, because of this part of the current, it is minus 90, minus 90. So, it is minus 180 degrees. So, you get some voltage which is 180 degrees from the current. Okay, so that's what gives you out of phase voltage or a negative resistance. Okay. Now, of course, that's not the only current flowing through this, and that is not the total voltage that appears at the output, but that's part of it. So that gives you a negative resistance. Okay. And if you do the analysis, it turns out to be if I call this C1 and CL. What was the other part? This I will give you a voltage 1 over SC1. So, is this correct? So, this is the negative resistance. Is this expression correct? Do you remember? So, This I gives you I divided by SC1, and that gives you I divided by SC1 times GM, and that divided by SCL is the negative resistance part of the voltage. What is this part? It's a series combination of C1 and CL. So if GM equal to 0, meaning if this part disappears, clearly you will simply have the series combination. So that is again something that you should check, right? You do get it that way. Okay. So what is this thing? So first of all, yeah, the special thing about this is that you have a negative real part, negative resistance. So what? Is it useful? Is it harmful? We don't yet know what the circuit is, but I already told you that this is a transistor. So if this is a transistor, what kind of circuit is this? Common drain. Common drain, right? So I have the drain connected to ground. This is the small signal equivalent of a common drain amplifier. A common drain amplifier could be loaded by a capacitor. After all, it is used as a voltage buffer. Okay? And you will have a capacitance. It is the transistor's own CGS plus any other parasitic capacitance. Okay? So what does it mean? If you make a common drain amplifier and load it with a capacitance, the input impedance will have a negative real part. Okay? So what can be a problem with this? Yeah, so the thing is, if this is being driven by an amplifier, that amplifier is presented with some reactive load plus a negative resistance load. So with a negative resistance, it could potentially oscillate. Okay. For instance, the previous amplifier could be, in the worst case, something like this. Okay. Some transistor loaded by an inductor. So clearly you make a nice oscillator using this one. Okay. So when you use it as an amplifier, it's a problem. Now you turn the problem into a solution. So when you want to make an oscillator, you use this circuit. Okay. So you have, what is the principle behind an oscillator? You have a LC network, a tank network with loss, and you compensate the loss using a negative resistance. So the biasing arrangement is not shown here. Okay, this is just the signal picture. So first of all, you can add a capacitor here if you want. Anyway, the bottom line is you have some resistance, some inductance with some series resistance. And on this side, you have some capacitance with a series negative resistance. So if the negative resistance exactly cancels the positive resistance of the L, it can oscillate. Okay. Have you seen the circuit? Somewhere? Huh? This is what is known as a Colpitt's oscillator. Typically, you also have another capacitance here, because you also need to adjust the frequency, but with the combination of these things, you get a negative resistance as well as a tank circuit, and the tank circuit's loss is compensated by the negative resistance offered by this. Okay. So this is all there is in a Colpitt's oscillator. It was a very popular oscillator. It is still, if you want to make discrete oscillators and so on. Now, with very low voltages in ICs, in CMOS ICs, you can make oscillators in a different way. That's why now you don't see as many Colpitt's oscillators anymore. The second thing is, the last class I talked about the importance of fully differential circuits. It's hard to make a fully differential version of a Colpitt's oscillator. But otherwise, it's a very popular oscillator. If you want to make an oscillator in the lab, working for some radio or something, this is the oscillator to use. And instead of L and C, you can put a crystal there, and that can become a crystal oscillator. Okay. So this is just some miscellaneous information. The last part of the problem was, you express it as a parallel combination of C1 CL by C1 plus CL and something else. What does this come out to be? Do you remember what that is? So, I have to subtract so this is the admittance of the entire circuit, the input admittance, minus okay, this is the admittance without the GM. So what do I get? Sorry, this is CL. What is the answer I get? Huh? So it turns out to be, you can express it as, I won't go through the algebra here, but the impedance of this will be there will be a negative capacitance series with a negative resistance. What is the negative resistance value? What? C1 CL by C1 plus CL square, is it? Is this what it is? I think that's what it is. Okay. So it can be expressed as some positive capacitance that you see plus a branch which has a negative capacitance and a negative resistance in series. Okay. So this comes out of some mathematical manipulation. What use do you see for something like this? And just now we discussed potential use of this circuit and a potential problem with this circuit. Okay. Can you enhance the use or reduce the problem by splitting in the terms up like this? Potential problem was it loading the previous stage with a negative impedance. Potential use is presenting a negative impedance. I mean, it's the same thing, but we can think of it as either a use or a burden. Okay. So can you get rid of the problem because just because of this representation, does it help you to get rid of the problem in some way? See, the one thing is, if you compare it to the previous representation, this is a frequency dependent negative resistance, right? It depends on S. Here it is frequency independent. Hopefully that's what you got when you are solving the assignment also. Okay. So what use do you see for this? So I'll take what I had there is the impedance of this amplifier, right? And the impedance of this amplifier is the capacitance plus negative capacitance and a negative resistance minus negative conductance. Okay. Now to this I have okay. So what happens? You are left with only the capacitance. So if you are having problem with stability of some amplifier stages because one of the amplifiers is presenting a negative impedance, you can connect a positive impedance. And this representation helps you to calculate exactly what it is that you need to put. And in fact, you can put this because this is a fixed resistance, right? You know what the GM is, your bias rate. If you know the value of C1 and CL properly, you connect this and the circuit will become stable. That is, if it was unstable before, potentially it could have been like this. So now I connect a capacitance and resistance here, it becomes stable because I have cancelled off the negative impedance parts of it. Okay. This again was a pretty common technique with bipolar amplifiers. Is this clear? So this is something, I mean, you play around with the expression and you express it in some other form. Perhaps you can make some use out of it also, right? Again, this course is about analog design.